Justy Alicea, Fossil Preparation Lab Manager at the New Mexico Museum of Natural History and Science, and welcome to Mineral Mondays. A fossil preparator is a paleontologist who specializes in the extraction of fossils from the material they're encased in and their preservation. People usually think of rocks, but fossils can be buried in all kinds of material like amber or tar, which all present their own unique preservational advantages and challenges. Even though the fossils usually have the consistency of stone, some can be as soft as chalk, and they all tend to be prone to breaking. So knowing how to ensure they don't is as important as getting them out. It's my job to get them out of that material, put them back together, and ready them for researchers to study, or for display to the public, or to be housed in the museum's collections. I also train volunteers how to do this and manage the lab in which it's all done at the museum. On today's episode, we take a moment to consider the Western Interior Seaway. Some of us may have heard of this enormous body of water that was home to such legendary stuff of nightmares like plesiosaurs, sharks, and mosasaurs for almost 20 million years. Most people outside of the Plain States have it. But how do we even know this was a thing, and what do we know about it? Most who have flown over the plains can't help but notice how flat the land is all the way from Missouri to Colorado and wonder why. And why is this such fertile farmland? For centuries, the people that have trekked across the canyons, plains, and mountains of the interior of North America, from Mexico to Alaska, have come across shark teeth and fossils of other marine animals. But how can that be? In some places, the nearest ocean is thousands of miles away, and some of these fossils can be found on the top of mountains. You may be tempted to imagine there must have been a giant flood covering the entire area, but imagine for a moment, what if instead the entire land had once been under the ocean itself? But how? It's a mystery that took the help of many scientists in different disciplines many years to piece together. Scientists use the natural processes that are seen and studied today to make inferences about things humans can't see, such as events in Earth's history, or processes that can't be studied with the human senses, like the decay of atoms. Geologists specifically are scientists that read clues left behind in rocks to uncover the story of how those rocks got there and what they have gone through since their formation. We can observe the processes that form rocks today and under what conditions, and use these to interpret events that occurred millions of years before any human was around to witness them. For instance, rocks are laid in layers over successively older rocks. These can be seen as pages in the Journal of Earth's History. Every now and then, something gets stuck between the pages and becomes a fossil. Now, as noted by Paleontology Collections Manager Nicole Volden in the last episode of Mineral Monday, sedimentary rocks are formed when sediments, grains eroded from already existing rocks or pieces of once living organisms, accumulate, creating layers that would eventually be compressed into new rock. Sediments logically accumulate in basins. Oceans and lakes are the ultimate basins, as all rivers lead to them, a scientific observation we all learned in grade school. Dead animals get buried along the way, becoming fossils. We can see this in extreme when we see the Grand Canyon, where the Colorado River has slowly carved out one of the largest canyon systems in the world over millions of years, channeling millions of tons of sediments out to the Gulf of California. All of this accumulated sediment will slowly solidify under the weight of additional sediments, a process called compaction, creating new rock with a record of all kinds of fun stuff, like our trash and plastic, trapped within the layers. In the case of the Grand Canyon, the relatively young Colorado River has cut through thousands of feet of ancient rocks similar to those under New Mexico, and washed it out to the Gulf of California to reveal a marvelous succession of time, with fossils of every period from the Precambrian up to today. As rivers drain away the sediments of the plain, they reveal rocks laid during an age when dolphin-like reptiles swam the entire breadth of the Great Plains. It's these layers of sedimentary rock made of shale and limestone which provide us with the marine fossils people have been seeing since before recorded history. Shale, one of the most common sedimentary rocks, is a kind of rock formed from muds and clays in slow-moving water in lakes, floodplains, continental shelves, or lagoons. There is more than one layer of it covering whole swaths of New Mexico, telling us that New Mexico was underwater more than once in its history. As a matter of fact, we know that some or all of New Mexico has been underwater for at least 7 of the geologic time periods since the Precambrian. You can also see changes in the distribution of this shale over time. As the ocean advanced and receded and layers of sediment continued to be deposited over time, you can see the margins of these different depositional sediments shift, showing us how the coastline changed. You may be thinking that's all fine and well, but how then did it all get up above sea level? Well, we know that plate tectonics, discovered only in the early 20th century, occurs today just as it did in the past. The plates of the Earth's crust are always moving from the pressures of constantly upwelling molten rock. As this rock wedges its way up to the surface, mostly through mid-ocean ridges in the Earth's crust, and solidifies, it pushes the plates apart, forcing them to buckle or slide underneath one another in other places. This makes each plate a slow conveyor belt of planetary surface, in which on one end, surface rock is being created, and on the other, surface rock is being destroyed. This is why the continents conspicuously look like their edges fit together, because they did. Where the Earth's plates push against each other, we get serious geologic activity, such as earthquakes, mountain building, and volcanoes, as evidenced by the Himalayas, which were formed by the collision between the plates India and Asia sit on millions of years ago, and to this day are still rising 1 centimeter a year. The annual monsoons, wind, and rains wear these mountains and volcanoes down over time, washing their sediments via rivers and streams out to sea, seeding the waters around India with tons of the nutrients that power life. In the plains, we can track the layers of Cretaceous mud turned shale slowly making their way southward, creating an arm of the Arctic Ocean. From the Gulf of Mexico, another arm of shale, originally an extension of the Tethys Sea, slowly crept northward to meet this. At the same time, we begin to see the uplift of the Rocky Mountains as the oceanic plate begins to subduct or go under the western edge of the continental plate of North America. As the plate slid under North America, moving eastward from the Pacific, not only did the top layer of it get scraped off by the North American plate riding on top of it, adding land that would become California to the west coast of North America in the process, but it began to push up the entire plate, the leading edge of which pushed the middle of the entire plate down below sea level as deep sea basins lost volume, pushing up oceans and raising sea levels. The gradually intruding waters split the North American continent in two during the late Cretaceous, 95 to 68 million years ago, with Laramidia to the west and Appalachia to the east, feeding in nutrient-rich sediment. There are many trace fossils of footprints of animals walking the coast of the Seaway that can be found in New Mexico in rocks of this age. When the entire area was lifted above sea level in later stages of the formation of the Rocky Mountains and ocean basins expanded, the waters drained, leaving behind rich, fertile soils that were eventually overtaken by grasses and herds of animals grazing on them. We can still see all of the geologic activity from this today on the west side of the continent, all the way from where the relatively straight leading edge of the entire Rocky Mountain chain steeply dips underground, forming awe-inspiring hogbacks and flatirons, followed westward by mountains, hot springs, volcanoes, and magma plumes beneath the earth, all the way until you get to the faults on the coast of California, where you reach the very same ocean plate that is sliding under the North American plate. Much of this geologic activity covered whole swaths of New Mexico's surface and volcanic rocks, burying many of the fossil-rich layers beneath them. And thanks again for tuning in to today's Mineral Monday.